All right, so for the next slot, we have our very own Jan talking to you, teaching you about the basics in BASIC. Give a warm welcome to Jan.
On. There you go. Thank you for letting me know. Hi, I'm Jan. Let's go back. Let's go back in time. 1985. Who in here is born after 1985? After. Okay. To me, that's kind of mind-boggling, because I used to say that I can't comprehend people being born in Germany and not witnessing the Berlin Wall fall, because it was such an iconic event for our lives and what it means. And nowadays you have to deal with people who weren't alive to see the Twin Towers fall, and like that was another, and those people are now like actual adults, and it really, that doesn't compute to me. We'll get back to 1985. Let's go back even further. So 1975, 1 year before I was born, I told you I was old, we started to see sort of the beginnings of somewhat of a home computer market. Home computer like nobody uses the term home computer anymore, because we have like these little things in our pockets now and everything. But yeah, the distinction was a computer that you could actually have at home, in contrast to these rooms full of equipment at big corporations, right? So computers were big back in the days. And so this is the Altair 8800. It is one of the first sort of kind of commercial home computers. It was sold as a kit, so you had to solder it yourself. It has it's very interesting in the sense that it doesn't come with any software out of the box. So you start it up and it's like the CPU is in a halt state and you have to do something, and then you have these flipping switches and you can program in stuff into memory with these flipping switches. You can buy one of these today based on an Arduino as like a replica with like a front panel. I just ordered one because I find it so fascinating. And so this is sort of the beginning. And then a couple of years later, we got the first wave of actual commercial home computers. And like if you have not been able to avoid the absolute barrage that is retro computing on YouTube, you've probably or if you're old enough, one of those, you will probably recognize a couple of names on this slide. And there's a reason why I like these systems. They are really, really simple. Like I said, the Altair, it started with something like 4 kilobytes of memory, and then you could expand it, but and the thing with these computers is I think they are the last generation of computers. I feel very uncomfortable. Give me a second. Don't know why. So this is the last, to me, the last generation of computers where a single human being can gather a complete understanding of a machine. And I mean complete in the sense that you understand the hardware, you understand how it works, you completely can understand the software, you know down to the milliseconds how many cycles a certain instruction takes and all of these things. And people, I'm not that person, but those people exist and they still do amazing stuff on these computers today, which is mind-boggling to me. So coming back to 1985, this is the year the Commodore Amiga 500 was released, or the 1000, I'm not entirely sure. And a couple of other computers like the Atari ST and I think the Acorn Archimedes is not far behind. And they sort of complete that transition from 8-bit to 16-bit. And you had the IBM PC already in the market at that time. And I think that's a point where the operating system gets so complex, the systems themselves get so complex that it becomes impossible to keep that all in your head. And processors become so complex that it's impossible to understand what they are actually doing. My first computer was the Commodore C64. I got it relatively late, so I'm not that old, but I'm old enough to still have one of those. And when you switch the Commodore C64 on, there is BASIC. BASIC stands for Beginner's All-Purpose Symbolic Instruction Code. Rolls right off the tongue. And it is old. It is much older than the C64. It was created in, yeah, thank you for recognizing my great puns here. It was created in 1963 at Dartmouth College in the States by John Kameny and Thomas Kurtz. And what they tried to do is they had these students, mostly non-computer sciencey students, and they wanted to create a language for them to be able to program on these multi-user systems. And originally it was a compiled language, so these multi-user systems, again, we are talking about these things that take up complete rooms, or later on, like at least like fridge-style computers. And BASIC is essentially a sort of more readable, more understandable version of Fortran. Fortran leaks a lot of the underlying machine details and is really complicated to read sometimes. And so BASIC was created for that, and then because it was a very basic language in the literal sense, it was easy to port it to smaller computers with less memory, and then people wrote interpreters. So because, if you think about it, if you need to compile something, you probably have a hard drive somewhere or some other medium you can compile to and everything. And those microcomputers, they had memory, that's it, right? So that's one thing why this happened. And the author I showed you earlier is actually relevant in the sense that it was the target for the first products that a small company named Microsoft brought out. And that's BASIC. Altair BASIC was a product originally developed by Bill Gates, Paul Allen, and with some help of Monte Davidoff. And most home computers back in the day, or microcomputers as we used to call them, have some version of Microsoft BASIC. Not all of them, some had their own implementations, everyone had some BASIC, but Microsoft BASIC is really on these devices a lot. And again, this is Commodore BASIC, and that's what we're going to talk about today. Here's an example. How many of you, like show of hands, who has actually programmed in BASIC once? Okay, a couple of hands. So this is, you can probably understand it, like just from reading it. So there's a for loop. It's a very simple for loop. It goes from 1 to 10. It prints a number, and then the next command is basically the end of the for loop. And then there's also an end. That end is optional, but it signifies the end of the program. And sometimes you need it because below the end you have subroutines and everything. What stands out here? Well, first of all, BASIC is loud. Fortran was loud, BASIC is also loud, everything is uppercase. There were variants that had like the possibility to also write it in lower caps, but it looks weird to a modern day programmer, I think. We have very short variable names. I know this is a bad example because we're still using the I for loop variables, but you can only have 1 or 2 letters in a variable name in Microsoft BASIC. So that's a bit of a problem. At least you can use numbers for the second letter, so that's good. And then, obviously, very alien to modernize are the line numbers. And I didn't put them on there to show you the actual lines. That's part of the program. So there are a couple of reasons for that. First of all, Microsoft BASIC doesn't have any labels or jump marks or anything, so you need to have some way to address certain lines. But then also, we're dealing with computers who don't really have good editors back in the day. And so let me show you a quick example of how that works. So this is how the computer starts up. And at some point, I'm going to start typing, I hope. And then I enter the line number. I enter the line. And then when I hit return, the line is actually entered into memory. And it doesn't look like that. It's like there's nothing specific happening. There's no message that it actually works. But you can't really, like, I can't really go up now and edit a line or something. That's not how that works. But I mean, it works. It's a running program. And so by having these line numbers, you can easily, by just typing the same line number again, you can just change a line that you've had before. So that's how that works. And it brings me to an interesting point, just a quick tangent. If you think about it, like modern development workflows. So you start up your editor, and then you have your program, your Ruby program or whatever, in the editor. There's probably a couple of dozen representations of the code in memory for like syntax highlighting and coding tools and whatnot, like refactoring tools and everything. And then you save that to disk, and then Ruby loads it from disk into memory, has probably another representation, which is like an abstract syntax tree or something, and then something, God knows what, happens, and then you can run the program. Whereas in Microsoft Basic, it's in memory once. That's all, right? Actually, if you really want to be pedantic, twice, but we're going to get to that. Here should be a video of me using a machine monitor, so I'm going to do that with a live demo. I'm trying at least. So this is now an actual emulator running, and so if I put in a program here, print hello. The cool thing of this being an actual emulator with additional software is that I can press a button and hopefully the window, I didn't change the font size, I'm sorry about that, but I'm going to show you the actual output later on and bigger. But what I can do now is I can take a look at a memory address because I know which memory address the program is at. And now you can stare at the basic program in memory. And that's kind of neat. And now we can take a look at how that actually looks. So let's go back to the slides for that. Because let's go back to the slides for that. There you go. So this is the, I marked out a couple of the addresses. So we start with a 0. There are reasons for that. They are kind of dodgy, but there are reasons for that. And then we have 2 bytes, which are a pointer to another memory address. And that memory address is what we have here. 8. So it's the wrong way around because of the way 16-bit addresses are encoded here. So we're going to 8.1c. So that's somewhere after the 00 there on the second line. So that's a pointer. So if you know your data structures, that's a linked list. We don't usually deal with these anymore, but that's what's used here. And then after that, we have the line number. And that line number is 2 bytes as well, because you can have line numbers that are bigger than 255. And so the line number is 10 in this case. If you're wondering why I use 10 and 20 and 30, it becomes quite obvious if you think about it. It allows you to insert lines in between later on, because otherwise you would have to renumber everything. There are ways to do that, but yeah, that's why. So the line number and then the 99. And the 99 is a so-called token. You can detect tokens by finding out that the 7th bit or the most significant bit is set. So everything above 7F in hex is a token usually. And 99 is the token for print. So that's the command that I use there. And then after that is actually quite easy to understand. There's a 20 is the space character if you know your ASCII tables. 22 is the quote, the double quote, and then hello Baltic Ruby. I'm sorry I didn't adjust for that. Hello, there should be hello Ruby on conf, I'm sorry. And then somewhere you'll get the 22 again, that's the closing quote, and then a 0, and that 0 just marks the end of the line. And so that's how a line looks in memory. And then there's another line below that, and then that line points to 0825 or 25, and that just points to 2 zeros, and that marks the end of the program. Done. So this is the code that turns the beginning of the code that turns the input that we done when you hit enter, turns it into tokens. I'm not going to explain this code. I'm not going to read it to you. What I wanted to show you is that this is a website that you can actually go to and read through not only the disassembly code, which is on the left-hand side, and you're going to see a little bit more of that later on, but also the original source code from Microsoft, which is the yellow stuff, and then up to 4 different commentaries from other people, and you can switch them on and off on the website. So this is my source that I've used to understand what's going on. It's really helpful. It sometimes contradicts itself because, you know, the errors were made, but it is really fun to read for some definitions of fun. So yeah, behold, we're going to take a look at 6502 assembler. Don't be afraid. So, this is centered and shouldn't be. It's bad. So this is the first part of basic warm start. Basic warm start basically means you've entered a line, you hit return, everything is done, and you're back to the beginning and you can start typing again. So the first line, well, actually, let's talk about something first. So assembler language. Assembler language, if you like, how many in here have written actual assembler code at some point? Like university, probably. So 68,000 or something like that. It's been a while, but so the 6502 is a very simple processor, as I said, and the way assembler language usually works is that you're working with either memory or registers, and registers are just basically also memory, but sitting directly on the CPU. And so on the 6502, you have a couple of registers. You have the program counter, which just always points to the actual point of execution. Then you have the stack pointer. The 6502 has like a built-in concept of a stack, and you don't have to manually manage it. It's only 256 bytes long, which is a bit of a bummer. And restricts a lot of what you can do. And there are instructions to kind of push stuff onto the stack and pull it from the stack. Stack is a very typical concept in the CPU as well. Then you have the accumulator, which is the register that you use for all kinds of calculations. You have X and Y, which are 2 registers to do loops and stuff, counting loops and everything, addressing memory directly, indirectly, and stuff like that. And then you have the status register, and the status register is comprised of 7-ish bits, which sort of save a bit of state, and we're going to see how that works in a second. So JSR is jump subroutine. And so the main code starts with jumping off to a different place. We're not going to take a look at that because that's another whole can of worms. But what that routine does is it waits for the user input, and then when you hit enter, it actually gives you back a pointer to the memory where that stuff is stored. So that's what we're taking in X and Y, and STX and STY. What they do is they store the contents of the register into memory. Now, the memory here is addressed in a short form because it's only 1 byte, and that's the specialty of the 6502, which is called the 0 page, which are the first 256 bytes of memory, which are easier to address. It goes faster, you don't need that much space for the instructions. By the way, I didn't explain the format here. So the first column is the memory address, where the code actually sits. And then you have 1 to 3 bytes that actually make up the instructions in memory. So every instruction has its own sort of value in byte form. And after that is the disassembled code, like what you would actually write in an assembler. Then we jump off to another address. Interestingly, this one sits in 0 page as well. So it's a routine that has been copied on startup from ROM to RAM so that it makes handling a little bit easier. And what this does, it gives you the first. So this routine on 73 is called char get, and it gets you the next character in memory and saves it to the accumulator. So we're then saving. Memory map, real quick. Because we have 65 kilobytes of RAM, but the CPU can only address 65 kilobytes. So what do? We do memory mapping. So we can switch out ROM parts and RAM parts in and out of the memory space. And so you can run your basic program, like you run your basic programs that are sitting in RAM and they are using code that sits in ROM, which is why you can't use the full memory in basic programs. But then if you write assembler code, you can actually switch out the ROM because you don't need it and can use more of the memory. And then you also have things like the I/O registers, which actually drive sort of the other hardware of the machine, and it's just memory addresses. So for example, to change the color of something, you just push something into a memory address. On some level, modern hardware works the same, it's just that we never see that. So let's go back to the code. So we got the character in the accumulator, we save it into the X register because why not? And then and then we figure out, like, is the byte that we got, is that actually a null? Because that means that the user just hit return on an empty line. And if we do so, we just jump back to the warm start in the beginning. It's an address that sits slightly above the code I have here on the screen, but it's doing the same thing. Then we store -1 into the X register because -1 is a line number that doesn't make any sense, and it could be that we're running on, like, we don't need the line number. So that's what we do. We store that in memory as well. That memory address is always holding the current line number of BASIC. And then we do something really weird, which doesn't make any sense if you just look at this piece of code. BCC is a branch on carry clear. So carry is one of those status registers, but nothing that we've used here would set the carry register. So what you need to know is that charget actually sets a couple of different flags depending on the data type that's coming in. And so carry clear just means so if the carry bit is not set, we are not looking at a number character. And with number character, I actually mean from, like, the actual character 0 to character 9. Because if we have a number character, no, wait a second. It's when the carry bit is clear if it is a number. Because if it is a number, someone just entered a line with a number in front. But what we can also do is just enter the commands without the line number, and then it will just be executed, which happens in the next few lines, which is the crunch address, which is the tokenizer. And then if we have the line tokenized, we can just execute it, which is called gone for some reason. Not going, but gone. Okay. The tokenizer, I'm not going to show you the code for that. I'm going to show you some Ruby code real quick. And I'll give you a quick example of what's happening. So this could be a line that's put in. So this is how it looks in memory. So again, you have the 99, the token for print, and let's make it run. So sorry, we'll get through that. There you go. So I just want to check that this clock works the same way as that clock. So we get another character. We're jumping to 73 again. So what I'm going to explain here is the way the basic interpreter figures out what to execute for a certain command. So we're jumping to this line for some reason. It will become apparent later on. And so we are, what's happening on this line here? So tokens, as I said, start at 80. So we want to have a number that goes from 0 to something. The reasons will become apparent. So we just subtract 80 hex, and then we jump over a couple of stuff that is not relevant here, and then we multiply that by 2. That is called ASL, which is shift left. So if you know your bit mathematics, if you shift a number left 1 bit, it's going to be times 2. So we now have a number that is is double the size because we have a jump table in memory that stores all the locations for all the different routines. And that one needs 2 bytes because we have a memory address. And so that's what's happening here. So now something interesting happens. So we get the address out of the table, which is this sort of indexed load thing that's happening here. So it's something, something, comma, y, which means the address I have here, which is A00D, is then added to the Y register, and now I have a new address that I can load into the accumulator, and I'm going to store that on the stack. So now the stack contains 2 addresses. One is our original return address, which I forgot to explain because what JSR does, the jump to subroutine, is that it saves the return address to the stack so that when you return from the subroutine, it can pop it and just hop back to that place. And so now we have 2 things on the stack. And then the first one is the address of the print routine, and the second one is the loop that we had above. And now what happens next is that char_get is actually a subroutine, but if you look closely here, we're jumping to it. We're not using JSR, which means there's not going to be an additional address popped onto the stack. So this is a trick that happens a lot because the 6502 doesn't have a way of jumping to an address that is actually saved in memory. And then print has also an RTS, and that's going to pop the other address that we had on the stack, and we're back in our loop. I'm going to, because I'm out of time, I'm going to skip over a lot of stuff. I just want to show you one thing that I did. So this is an expression, right? So print could output any mathematical expression as well. So what do I do to evaluate that? And that code actually broke my brain a little bit because it is complex in every language if you think about it. It is not a difficult problem, but it is a complex problem because you have to think about precedence in mathematical operations and all of that kind of stuff. So here is a quick video of what I did to explain what's going on. So there are 2 functions in play here, which one is called form_eval, which is the routine that actually tries to evaluate the full expression. And then there's eval, which only will give you back 1 value. And then stuff lands on the stack. This is the precedence value down there. And now we're getting the rest of the stuff. Now we're popping things off the stack. Now we're calling the addition routine. We have a result. That gets passed back a couple of times. Then we have the multiplication. That one goes onto the stack with a different precedence. Then we evaluate 5. We have a plus, but now an interesting thing happens because the plus has a lower precedence, and so we're evaluating the other part first. And then we're getting back to the 20. That's now sitting on the stack. We're evaluating the contents of the SYN. The xy is a variable that I've conveniently set to 0, so that doesn't become too complicated. And now we only need to unroll the stack, and boom, we have a result. So that's how that works. So again, that really nearly broke me. So some interesting facts here before I go off. All numbers are always handled as floats, which is ridiculous because the processor doesn't have any way to deal with floats, so it's all manual code and it takes up a lot of memory, but that's what they decided on. So what about integers? They are integer variables. They have a % sign at the end. They're just like, when you save them to memory, they save space, otherwise they're just handled as floats. Okay, so some more code, because it doesn't make any sense to take a look at it. And then again, I'm out of time. I want to get to one thing here in the end, and then I'll head off, because I want to thank I obviously need to speed up the talk a little bit. That's good. I want to thank a couple of people here. One is Michael Style, who created pagetable.com, which is the stuff I told you earlier. And then Lee Davidson also did a commented version of the whole ROM code. And those two things helped immensely. And I hope that wasn't like completely over everyone's head. I feel a bit weird standing here now, but yeah, thank you very much.